Are really large numbers relevant for us biologically? Yes. Okay, we're always talking about a lot of receptors in real life, a lot of cells, a lot of whatever it is. Okay, so as numbers get really, really large, okay, this is what we actually care about. So this was back to our coin flipping example. Okay, we had you flip a coin 4 times. Your only options for binomial are heads or tails. Okay, and then we have number of heads here as the possible outcome. So there's one way to get no heads, one way to get 4 ways to get 1. There were 6 ways to get 2 and 2. Okay, so you could plot it like this. You could plot multiplicity versus the number of heads. Okay, in this case, I've let heads be my outcome of interest. What does this curve look like if I flip it 10 times?
More same.
Have same, more rounded. What's happening to the scale of the y-axis, do you think? The range is larger. Okay, so here we went from here's 0. There's 1 way to get 0 heads, 4 ways to get 1, 6 ways to get 2. If we raise this to 10 flips, this now to get 5 out of 5, there are 250 ways to get 5 and 5. And I think we understood intuitively that it's vanishingly unlikely that you'd actually flip heads 10 times in a row. Like, we know that. This confirms it. Here's what it looks like for 200 flips. Here's like what it looks like for 1,000. Okay. When the outcomes of a binomial distribution have the same probability, okay, so the odds for your probability are 50-50 for your 2 things. The highest multiplicity is the most likely outcome regardless of number of trials. It doesn't matter how many you go. The center of this will always be the most probable outcome. Okay. So in the case of coin tosses or any other binomial process, and this equal probability is really essential here, because if you don't have that assumption in play, then this is no longer valid. Okay? We're not going to just center it anymore. Okay? The outcome with the same number of heads and tails will have the maximum multiplicity, n would be equal to m over 2, and 311 in your book is the proof for this. Okay, so let's talk about relative probability. All right, so once again, when you have a binomial situation and the 2 options, on, off, fold, unfold, bound, unbound, head, tails, are equal, okay, then maximum multiplicity will be when n is at m over 2. M being total outcomes, total flips, total receptors. Maximum multiplicity will be at the halfway point. Okay? Relative probability of 2 outcomes, okay, can be determined from the ratio of their respective multiplicities. Again, this is only if the binomial outcomes are of equal probability. So if you flip a coin 10 times, 10 is the number of tosses. Here, the number of successes, or the number of heads, if that's what you're interested in, is 5. So here we have a multiplicity of 10 tosses getting 5 heads. What is the multiplicity? How many different ways can you get 6 heads and 4 tails? So if you, do I want to write it out for you? Where's my marker? So hopefully everyone understands this is 10 factorial over 5 factorial, 5 factorial, and then I'm dividing. When I want relative probability, I want you to take a ratio. Anytime you see the word relative probability, there goes my earring. Little like, 6 and 4. So this can become 10 factorial, 5 factorial, 5 factorial times, instead of taking, doing the division, I'll flip them over and multiply them. This is going to drop out. This is 6 times 5 times 4 times 3 times 2 times 1 times 4 times 3 times 2 times 1. My bottom is 5 times, you get it. It simplifies to 6 over 5. Or 1.2. Okay. If I flip a coin 10 times, it is 1.2 times more likely that I will get 5 heads than I will get 6 heads, okay? This is the way to interpret relative probability, and I want you to keep in mind that taking the ratio of just multiplicities only works when it's 50-50, otherwise we have to properly calculate probability and then take a ratio of the probabilities. The simplification to multiplicity only works for this. If we go up to 100 tosses or 1,000 tosses, again, those odds change, okay? So it is 7.34 times more likely that if I flipped a coin 100 times, I'd get 50 heads instead of 60 heads. Or 5.44 times 10 to the 8th times more likely that if I flipped a coin 1,000 times, I would get 500 heads instead of 600 heads, okay? The more tosses you do, the less and less likely it is you can get away from the center of the distribution.